Okay, so we got all the things that people are scared of in linear algebra. We got row vectors, column vectors, and matrices, and we're combining them. What does it mean? Let's see what you guys said. Reveal submissions. It represents the blank. Some people said probability. Some people said expected value. Some people said probability at time t, which is like an extra specific version of probability. Probability is absolutely correct. So if you said probability, you're correct. Expected value can also be correct if you put the right function. So it turns out all probabilities are expected values, but not vice versa. We're going to see how you can make the expected value thing correct in a second. So you might also have it right. And I will say probability at time t is even more correct than just probability. So that's very nice. The probability to be at blank, where are you? 9 or the last state, those are both the same, or state 9. That is the last space, very good, last space. So it is the probability to be at the last space, and specifically at time t. So this 0 and a 1 is kind of representing the last space. And starting from, where do we start? Square 0. So this row vector over here represents the starting, so 0 or square 0. If you said position 1, you're probably also thinking the beginning, but you have the 1s and 0s mixed up. Python also always starts at 0, not at 1, so make sure you don't mix that up on your assignment. Yeah, so it is the first space on the board, but the first space is square 0. Okay, very good. So I think most people more or less got it. And by now, we actually have multiple different ways to think of this problem. Probably most of you guys did it by thinking of probabilities. So let me show you that way of thinking. So we are doing 1, 0, 0, 0, 0, p to the power t times 0, 0, 0, 0, 0, 1. And you can think of this thing as the starting vector, p0, the probability vector at time 0. And then if you combine these two things, p0 times pt, we said that that is p sub t. That is the probability vector at time t. Prob vector at time t. So that is what we did last, maybe 2 classes ago now. So on the first time we did snakes and ladders, and that, some people call this the forward equation. So this is the forward equation way of thinking. Forward equation way of thinking. So you combine the matrix and the row vector. The row vector is a probability at, you think of it at time 0, multiplying by the p matrix to the power t, moves time forward by t steps. And the matrix exponent is the number of times you do it. So multiplying by p once moves 1 step, multiplying by p to the t moves t steps. So you're now at time t. Where are you? It's random, but it's in that probability vector pt. And when you do this row matrix combination, this is what we said is, last class, we said is unexpected value. So this will be the expected value of something at time t. So this will be the expected value of something involving st. Okay, so last class I did it with the vector. We did this vector. We did pt times 0, 1, 2, 3, dot, 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 9. And that expected value was the expected value really of st, of just the position. This class, I'm doing with all 0s and a 1, and it's actually the expected value of something that is sometimes 1 and sometimes 0. And if you do it, the right way to say it is it's the expected value of this vector. Let's call this vector v. It's really v of st. V of st, where v is this vector. V is this vector. So, and by that I mean you got v0, v1, dot, 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 all the way up to v9. So a vector of length 10 you can think of as a function, v0, v1 to v9. And we're doing the expected value of v of st. That's exactly what we did last class, except it turned out last class that v of st, v of s was equal to s. So when you do the expected value, you just get the raw number. So by putting in 0 to 9 last class, you get the raw numbers, but you can put any number you want into this vector, and it will work perfectly fine. And it turns out in this situation, v is only 1 in one situation, right? It's all 0s except 1, right? So this is equal to what is the expected value of something that is sometimes 0 and sometimes 1? Well, it's the probability that it's equal to 1. So it's the probability that v of st equals 1, which is also known as the probability that st equals 9, because that's the vector we're talking about. It's only got a non-zero thing in the last component. So that's the way to interpret this thing. It's the function, which is all zeros except a 1. So what is it on average? Well, if you're in the last component, you get 1. Otherwise, you get nothing. So it's just the probability you're in the last component. So that's kind of a combination of what we did 2 classes ago and what we did last class. Getting this thing is a probability. So if you said probability and you meant this, that's right. If you said expected value and you meant this, that's also right. It's both. It's the expected value of a function that is 1 or 0, which is also a probability. Questions or comments? Okay, so last class, we had these kinds of combinations, and I mentioned that you can actually do the whole thing this way. So instead of thinking of probability vectors, you can do the whole thing sort of using this kind of expected value. And that is the sort of backwards equation way, which I briefly mentioned last class, and I will go into a bit more detail now. In the backwards equation way, so you start out, again, we're doing the same thing. So we're same problem. 1, and then all zeros, and then p to the t, and then this vector is 0, 0, 0, 0, 0, 1. But instead of combining the first two, you can combine the last two. Okay? So you think of 1, 0, 0, this row vector of being probabilities, you keep that as it is, and you say, what happens when you multiply by the matrix P to a column vector on the right? You're doing multiplication with the matrix on the left and the column vector on the right. And what this will be is this will equal, so 1, 0, 0 is unchanged, and it's this vector of expected values. So it's the expected value of v of st given s0 equals 0, the expected value of v of st given s0 equals 1, dot, 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 all the way up to the expected value of v of st given s0 equals 9. So it's a vector where the components are all different expected values starting from different points. And this is what I called the Kolmogorov backwards equation. So let me state it more precisely and prove it now. So the proposition is that if v is a vector equals, so it's a vector and it's made of applying the function v, v0, v1, all the way up to, let's call it vn, so that we can do it for n states, is a vector made from a function v, all right, v dot, like that. So it's a function. So there's a function that inputs states in our Markov chain and outputs numbers. I guess if you were very fancy, you'd write it like this: v from fancy s, the set of states, to r. Okay. Then, and what I'm going to prove is that if you multiply p times v, you get exactly what I said over here at time 1. So it's the expected value of v of s1 given s0 equals 0, dot, 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 all the way up to the expected value of v of sn, not sn, s1, always 1, 1 given s0 equals n. So it kind of moves the expected values forward in time by 1, right? So in the Kolmogorov forward equation, the probabilities were getting moved forward in time. And in this one, the expected values are getting moved forward in time. So it's just two sides of the same coin on how you think about it. And the proof of this is very similar to the proof we did before. You just write out what does it mean to do a matrix product. So you write out what this is, and it's going to fall right out. So let's do the proof. The proof of the proposition. So what I'm going to do is I'm going to take the 8th component. Look at the 8th component of the left-hand side. And the 8th component of the left-hand side is a matrix vector product. And we want to know the 8th answer, PV sub A. Well, that is equal to the sum of PAB times V sub B, right? And B is going from 0 to n, summing over the states in our Markov chain. And these are probabilities. Remember, the PAB is the probability to go from A to B, which if you're going to write it as a probability, it's the probability that S1 equals B given S0 equals A. So you start at A and you go to B. On the other hand, what is VB? That's the Bth component. That is V of B. All right? So you multiply the value V of B times the probability that S1 equals B, and you add up over all the B's. That's exactly the expected value. Some people give this rule a really funny name. They call it the law of the unconscious statistician, which is a silly name. I don't really know the origin story of this. Why is he unconscious? I don't know. Unconscious statistician. So this is equal to the expected value, right? So we're adding up the value times the probability added up over all the possible states. That is exactly what the probability, the expected value means. Expected value, and it's V of S1. And the point is that S0 equals A is always the same here. So you're just doing conditioning on S0 equals A as your starting point. Okay, so that's the 8th component. And the general statement is look at all the components all at once as a vector, right? So you can either do it component by component or as a vector. Either way, that's the story. Questions or comments about the proof? So this is the Kolmogorov backwards equation, which again, it's just using basic facts about probability theory. Okay. All right, so now we have two different ways to understand this problem, the forward way and the backward way. There is one other way that I will show you now, again, very similar to this thing, which is in this specific case, when you have a vector of all ones, or sorry, a vector with a 1 and all zeros, what you are actually doing is pulling out an entry. So this is the third, here's the third way to think about it. The third way. The third way. And this is also useful to think about. Sometimes if you have 1, 0, 0, 0 times p to the t times 0, 0, 0, 0, 1, this is actually the entry. This is one of the entries of the matrix P. It's some entry, the question mark entry. And that's because when you multiply by a vector with has a 1 and all zeros, you're sort of pulling out a row. So when you do this times this, you're pulling out a row. And when you do a matrix multiplication like this, you're pulling out a column. And if you pull out a row and then you pull out a column, you're going to just have an entry. So this is like a basic fact about linear algebra. I mean, in fact, when you do multiplication like this, you're doing a linear combination of the rows of the matrix. So this is saying, please do 1 copy of the first row and 0 copies of all the other rows and add them together. If you do 1 copy of the first row and 0 copies of all the other rows, you just have the first full row. This is saying, do 0 copies of all the columns except the last column. Do 1 copy of the last column. So this is pulling out entries of the matrix by pulling out a row and then pulling out a column. And in this situation, it's pulling out the 0, 9 entry. The 0, 9 entry. And that's because this is the 0th entry over here, and this is the 9th entry over here. And that's why we got 0 and 9. So it's saying, give me the 0, 9 entry. And it turns out that P, if we did just P0, 9, like if T was equal to 1, that would be a nice probability, right? And it turns out this one is a probability too. This is something about the probability of something being 9 given that you started in state 0. That you started in state 0. And in this situation, if it was just S1, that would be just the regular P. So when T equals 1, it's S1. But in this situation, it's ST. It's ST. It's the Markov chain after T steps. And the big identifier here is that PT is actually the Markov transition matrix for the T-step process. So PT AB equals the probability that S sub T equals B given S0 equals A, right? So just 1 copy of the matrix is doing 1 step, T copies of the matrix are doing T steps. And you can check this by either of the ways we did before. You can either do it with the forward way or the backward way and see why it's true. But this is sometimes useful to think. So instead of thinking of stakes and ladders 1 turn at a time, you can multiply the matrix by itself and think about it 10 turns at a time, right? And take it to the power 10 and do a bunch of steps all at once, which can be useful sometimes. So that's an equally good way of thinking about it, and look, it matches all the other things we've done. You always get the same answer at the end of the day. It's the probability, it's 9, and I guess I didn't write that you started from 0. So starting from this thing. Okay. All right, and this situation, exactly the same thing, because the v function was only 1 in the 9th component. So there you go. That's what we're doing. We're calculating the probability that you're at state 9 at time t by putting in those specific vectors. Questions or comments? Okay. The rest of the class, the goal, is going to be to answer the question from the original Numberphile video. And you might remember in the Numberphile video, they wanted to answer the question, how many steps does it take to finish the game? How many steps to finish the game? So how many times do you have to roll the dice until you reach square 9? And we haven't answered that, but we have the probability to be at square 9. And the probability to be at square 9 was this nice matrix power. Now we want to know how many steps do you need? Okay, there is a nice relationship between how many steps and this probability. So that's what we're going to do. We're going to say, we're going to turn this into a question. So let's give this thing a name. Let's call it n. I'm going to call it n steps. N steps. And n steps is a random variable equals how many steps it takes. So that's random, and we want to know what is it on average. So we write a big E, and we put the n steps inside. That's taking the average value of the n steps random variable. And there's a connection between this thing and the probability we just found of the probability you are at 9, say starting from 0. Okay. So that's what we're going to do. We're going to use the connection, and we're going to figure out how to do these things. And to do it, I'm going to do an even easier problem that you've probably seen before that shows you what is the connection between this kind of thing and this kind of thing. So connecting an expected value to a probability, how can you figure it out? And I'm going to do it for coin flips. So, and this is a problem-solving strategy I like to call, if you can't solve a problem, think of an easier problem you still can't solve. So here's an easier problem, which is we're going to flip coin flips, and we're going to make n equals the number of flips. Oh, I think I called it G. Let's call it G. G is the number of flips until the first heads. Okay. And we want to figure out what is the expected value of G. And we're going to relate this to probabilities involving coin flips. Probabilities, coin flips. Okay. And to see how much you guys know about this problem, which hopefully is ringing a bell, I'm going to ask you a question. All right, let me find the thing where the questions are. Here it is. Easier coin. Yeah, so this is the easier problem. So G is a random variable, which is the number of coin flips you need to flip until the first heads comes up. So G is random. Maybe it takes a long time. Maybe it takes a little time. But this thing has a special name. You might have seen it before. You might remember the name. And so it's called a blank random variable. See if you can remember. And this one has options. You either know or don't know why it has that name. I guess if you don't know the name, you don't know why it has the name. So there you go. Okay, I'll give you 1 minute. Try to remember, what is this thing called and where does it come from? Okay. All right, 10 seconds left. If you don't know, you can put I don't know. Again, I like fun guesses, so give me a name. Steven. Whatever you want to call the random variable. Okay. Okay. What is the name of this random variable? People said it's called half the people are on geometric. Some people are on Bernoulli. Some people are on negative binomial. I'll say discrete. I'll tell you right now. Discrete just means it is on like the integers or something. It's not so it's like discrete and continuous are types of random variables. That's not the name of the random variable. So some people think it's one thing. Some people think it's the other one. Great, fantastic name. I wish. I forget. Yeah. Okay. So I'll tell you what. It's one of these. But is it a geometric, a Bernoulli, or a negative binomial? I will let you revote. Let's do it again. And now you know some options. It's one of those three. Which one is it? All right, let me. Did I press the wrong button? Okay, think. I will reopen it shortly, and then we'll see what you guys think. Duplicate. Okay, I'm only going to give you like 30 seconds this time, so that you got to pick which one you think it is. Okay, 5 seconds. Get in your final guesses. I realize at this point in time that naming it G might have given away the answer. Let's see if people caught on to that. Yes, okay, it's geometric. G for geometric. It is the geometric. Bernoulli, so geometric obviously is named after like something to do with real life. We're going to see why in a second. Bernoulli is a famous dead mathematician, and Bernoulli just means coin flip. How famous do you have to be to get a coin flip named after you? So a Bernoulli is one of the coin flips. It's either 0 or 1, right? The first coin flip is a Bernoulli random variable. And G is how many Bernoullis until you get the first one. A negative binomial is something else. I won't say what that is in case I get it slightly wrong. But a negative binomial is like until you get a certain number of somethings. But the one we're looking for is a geometric. That's the right answer. And I suppose nobody knows why it's called that. Let's see. Yes, don't know. Okay, great. We're going to find out today. Why is it called a geometric? Yeah, because it's named after Mr. Geometric. No. Okay, we're going to find out. All right, let's continue. So the thing we want to do is figure out the average value. And I'm going to make things a little more specific. I'm going to say each coin flip has probability P of coming up heads. So each coin flip has probability P of heads and 1 minus P of tails. A regular coin flip is the case P equals 1/2, but we're going to find the answer as a formula depending on P. So the question is the expected value of G, the average number of coin flips you need. How does that depend on P? And here is method 0. This is, we did this already. It's the law of the unconscious statistician. This is the law of the unconscious statistician method. Stats. And what you would do is you would say, you add up this sum. So you say it's the probability it's 1 times 1 plus the probability it's 2 times 2. Okay, and I guess if you're going to write it like this, you don't put a sigma. If you want to write it with the sigma, you go like this. Okay, the sum of x equals 1 to infinity of x times the probability G equals x. This is the law of the unconscious statistician way of writing this thing. This G really doesn't want to come out nice. Okay, G, okay. The probability times the value. All right, that's what we did before. If you do it this way, it's quite annoying. So you get this sum. X equals 1 to infinity. X, the probability it's equal to x. I will do it very quickly for you. You don't need to know why, but it's 1 minus P to the power x minus 1, because you need exactly x minus 1 coin flips to come out tails, and then you do times P to the x. Okay, and that's times P, okay. Not times P to the x. You need exactly x minus 1 tails, and then you need 1 heads right at the end. That's the probability that the number of coin flips was x. And this sum is rather annoying to do because of this stupid x in front. This x is very annoying. You can do this sum, but it's a pain. I don't know a super nice way to do it that it doesn't use like generating functions or something complicated. So we're not going to do it this way. This is not the way we're doing it. This is to show you don't do it this way. We're going to do it a slightly smarter way. And the way we're going to do it, I'm not kidding, this is called the Darth Vader rule. Potentially even weirder than the law of the unconscious statistician. And I'm going to tell you what it is, and I'm going to show you sort of where it comes from. The expected value of g, it's actually, instead of summing up x times the probability it's equal to x, you can do this sum. You can do the probability g is greater than or equal to 1 plus the probability it's greater than or equal to 2 plus the probability it's greater than or equal to 3 plus ... So instead of adding it up with an equal sign and putting these x's in front, you can add it up with a greater than or equal to sign with nothing in front. Why does this hold? Why? Well, so there's one proof you could do is to rearrange these terms, but there's an even simpler proof that I'm going to show you here, which is to write g in terms of indicator functions. So I'm going to write it like this. It's 1. Let me just write 1. 1 times g is greater than or equal to 1. And I'll explain what this means in a second for those of you who have never seen an indicator function. Okay, what does this 1 mean? Where 1a means 1 if a happens and 0 otherwise. So this is called an indicator random variable. And it indicates, it indicates with a 1 if the thing happened, and it indicates with a 0 if the thing didn't happen. Who's seen an indicator random variable before? Okay, a few. Who's never seen an indicator random variable before? A few people. Okay, this is your first time. So, in fact, we had an indicator random variable earlier. Let's give an example. And we did it without saying the example. The function v of s from before was actually v of s was the indicator that s equals 9, right? The value function we were using, it was all zeros, and then it was 1, 1, 1 right at the end, and it's just telling you whether or not you're in state 9. If you're in state 9, it's a 1, otherwise it's a 0. And we even use the fact that the expected value of, if you do v of st, that is the expected value of the indicator function of st equals 9, that is the probability that st equals 9. So the expected value of an indicator function is a probability. If you want to know if something is either 1 or 0, what is it on average? Well, it's whatever the chance is of it being 1. That's what it is on average, if it's sometimes 0 and sometimes 1. We did that already. And you can see in my little proof here, once I can convince you that this equation is true, the reason the Darth Vader rule is true is by taking the expected value of the left-hand side and the right-hand side. So on the left-hand side, it's g, so it becomes the expected value of g. On the right-hand side, it's a sum of indicators that becomes a sum of probabilities. So all I got to do is convince you that this thing is true, and then the top line, it's the expected value of this. Okay, why is this crazy thing true? Maybe there's a question first. Okay, let's do an example. Let's pretend g equals 2. So say g equals 2. So when g equals 2, on the left-hand side you have 2. What do you have on the right-hand side? You got to add up the indicators. Well, is g bigger than or equal to 1? Yes, it's 2. So this one's equal to 1. Is g greater than or equal to 2? Yes. So that's a 1. Is g greater than or equal to 3? No. So you get a 0 here. And in fact, all the other ones will be 0 as well. So for no matter what g is, eventually this sequence is all zeros, right? Whatever g is, eventually it ends with all zeros. And actually the number of ones you have is exactly g, right? When g is 2, you have 2 ones over here. If g was 3, you'd have 3 ones over here. But 1 plus 1, 2 times, that's exactly 2. So no matter what the value of g is, this will always be true. We're sort of representing g in 2 different ways. One is g, and the other one is 1 plus 1 plus 1 plus 1 plus 1 g times. That's the same thing. So these two things are precisely the same, two ways to represent the same random variable, so they both have the same expected value. So that's why the Darth Vader rule is true. Like I said before, you can also prove it just by rearranging some probabilities. Maybe I'll send that out as a little bonus if people are interested. But there you go, the Darth Vader rule. Now we can use it to find the expected value of G. So that's why it's true and what it is. Question here before we apply it to the geometric. All right, here we go. So, and this hopefully will be an easier sum than before. This is our hope. So the expected value of G, it's going to be the probability G is greater than 1 plus the probability G is greater than 2 plus dot, dot, dot. Remember, G is the number of coin flips until a heads. Until first heads. Okay, and this has a nice thing. What is the probability G is bigger than 1? I claim it's 100%. You always need at least one coin flip until the first heads. It's impossible to flip coins and have it come up heads before you flip the first coin flip. So that's 100%. Great. What about the probability G is bigger than 2? That means you needed at least 2 coin flips. Well, it must have been that the first coin flip was not heads, right? If the first coin flip was heads, it would not take greater than or equal to 2. And so this is precisely the event that the first coin flip is tails. So as long as the first coin flip is tails, we don't care what happens after that. It's definitely going to take at least 2 coin flips. And this pattern will continue. So let's keep going. So the probability G is greater than or equal to 3. What will that be? Well, you need the first 2 coin flips. First and second coin flip are tails. Right? So if the first 2 come up tails, maybe G is 3, but maybe G is 100. For sure, G is going to be greater than or equal to 3. So those are exactly the same. And this pattern continues forever and ever. So what is the point of this? Figuring out if G is greater than or equal to something is actually easier than figuring out what's the probability it's equal to something, right? So it's all very nice. And in fact, this is a nice thing. The first coin flip is tails, that's 1 minus p. What's the probability the first 2 coin flips are tails? Well, you need 1 minus p for the first one, and then you need 1 minus p for the second one. So it's a 1 minus p squared, 1 minus p cubed, and so on. And we're finally at the point where we realize why this is named after Mr. Geometric. This is a famous sequence in mathematics called a geometric sequence. Geometric sequence. I guess technically we're adding it up, so it's a geometric series. But this is a geometric series, which is the sum of a geometric sequence. And this is why geometric random variables are called geometric. These probabilities are geometric. All right. So hopefully you've seen a geometric series before. Does anyone remember the formula for the sum of a geometric series? Yes.
1 over 1 minus whatever the rate is.
Ah, okay, great. Yes, I like this. This is amazing. 1 over 1 minus whatever the rate is. This is a super nice trick, right? If you do 1 plus r squared plus dot, 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 there's the trick where you multiply by r and shift it over. Hopefully you've seen it before. One of the nice proofs of mathematics. What is it in this case? I will let you think for a second. So it's 1 over 1 minus whatever the rate is. What is that equal to here? Okay, I'll let you think. Let me give you a minute to think and fill in what it is. Or you can try to remember why is it 1 over 1 minus the rate if you want. Okay. Does anyone want to share what they got? Yeah. It's 1 over p. That's exactly right. Yes. So it really, I mean, technically it's 1 over 1 minus p. 1 minus p like that. So 1 minus p, right? Because this is a geometric sequence going by 1 minus p's. So the rate is 1 minus p. And then the 1 minuses cancel in some sort of miracle. And you get 1 over p. That's very nice. 1 over p. What this means is, if p equals a half, a fair coin flip, how many times do you have to flip a fair coin flip until heads comes up? Well, on average, it's 2. 1 over a half. Makes perfect sense when you think about it. And you might be wondering, isn't there an easier proof of this fact? We're going to see an easier proof before the end of the class. But for now, this is the first proof we have that a geometric adds up to, on average, 1 over p. Now, let's go back to the question we actually want to answer. What is the expected value of the number of turns? In Snakes and Ladders, you're rolling the dice. How many times do you have to roll the dice until you get there? Can you write it out as a big series? Equals something plus something else plus something else. Can you figure it out? I'll let you think again. I think it's more instructive for you to think than for me to just tell you. Let me give you another minute. Can you figure out what's going to go over here? And then I will add it up. It kind of looks extremely similar to the geometric case, but slightly more complicated. Okay, I'll let you do it. Okay. So again, it's going to look extremely similar. In fact, you could say the thing we're going to get is also a geometric sequence. It's just that instead of taking a number to the power, like 1 minus p to the power 1, 1 minus p squared, 1 minus p cubed, where p is a number, it's going to be a matrix geometric series, right? We're going to have a matrix to the power t, and we're going to add up all the different powers. And again, the starting point is the same Darth Vader rule. So it's the probability that it takes at least 1 turn, greater than or equal to 1, plus the probability it takes at least 2 turns, and so on and so on. And these probabilities are exactly what we did in the warm-up question. They're exactly given by asking, look, if it's going to take at least 2 turns, then you just say, like, are you at the endpoint at time 2 or not, right? So this is the probability that S sub 1, if it takes at least 1 turn, that means S sub 1 is not equal to the final state, 9. And if it takes at least 2 turns, that means S sub 2 is not equal to 9, and so on and so on. Let me do one more. S sub 3 is not equal to 9. So this is a bit like, right, with the geometric random variable, we said, are you still flipping at time 2? Well, if so, then it's going to take at least that long, right? So there's a kind of a connection between how long it takes and are you finished at that time that we're using here. And we didn't quite do this on the warm-up. We actually did the probability S1 equals 9. So you got to fix it with a 1 minus. This is 1 minus the probability S1 equals 9 plus the probability 1 minus the probability S1 equals 9, and so on. So if you want, you can do it that way. S2 equals 9. And these are matrix powers. Okay, they are the matrix power. They are exactly what we started the class with. 1, 0, 0, 0, 0. Then you have the matrix p to the power t, and then you have 0, 0, 0, 0, 0, 1. Okay, so that's a number. You do 1 minus that number, and then you add it up over all times t going from 0 to infinity. There you go. It's extremely annoying that I have this stupid 1 out front. It would be so satisfying if I could just say it's a matrix power, and then I could be like really happy. But yeah, unfortunately it didn't come out that way. Yes?
I may be completely wrong, but like in my head, the probability of the number of terms being greater than or equal to 1 would
Yeah.
be the probability of S0 not being 9.
S0 is where you start. So that when I'm using this notation, I'm doing S sub t. So t is the time variable. So it's like how many turns into the game you are.
Yeah.
S0 is where you start. I will say there's one thing that's confusing is like I'm thinking of st as a number. Sometimes I think about vectors, and then the number is the component of the vector, right? So yeah, don't get mixed up. I guess capital S is the random variable. That's a number. Don't get it mixed up with like v sub 2, which is like something in the second component. Maybe that's the. Yeah, great question though. Anyone else? It turns out there's a nice way to bring this 1 in. Does anyone see how to bring the 1 on the outside? You can feed it in there. Here's how you bring the 1 in. I claim it's actually the same as this. T equals 0 to infinity. Same start, 1, 0, 0, 0, 0. PT, and then instead of doing all zeros and then a 1, I do all 1s and then a 0. 1, 1, 1, 1, 1, 1, and then a 0 right at the end. And that is the same. Why is that the same? Well, what would this represent if I have all 1s and then a 0? Remember, we said that's the value function. Imagine I give you $1 if you're on square 0, or on square 1, or on square 2, or on square 3, all the way up to square 8. If you're on square 9, I give you $0. This is like how much I'm going to give you. And I say, how much money do I give you on average? Well, it's exactly the probability you're not on square 9, right? If you're not on square 9, you get $1. If you're on square 9, you get $0. What do you get on average? The probability that you're not on square 9. So that's one way to do it. The other thing you could do is you could notice there's a nice thing that P times the matrix of all 1s is equal to all 1s. So all 1s is an eigenvector of the matrix P, and that's because we said that multiplying the matrix P moves the values over by 1 step in time. If you always get $1, then no matter where you start, you're always going to have $1. So this is another way to do it. But in any case, however you want to reason this out, you can write this very nicely, vector of all 1s and then a 0, and a 1 over here. So remember, this is the interpretations that we're thinking of is this is the start. This is the start probability vector. And like you could imagine, I don't know, like you're playing against your like little brother or something. So you're like, let me start. We'll let my little brother, instead of starting at the 0 square, we'll let him start at square 0 half the time and square 2 like half the time. Like we'll give him a handicap. You could put that in the starting probability vector. And this ending thing is the ending value. Vector. That's what I called V at the beginning of the class. And so if you combine these things with P to the power t, that's at time t. And if you add up over all the times t, that is exactly the number of turns on average, the expected number of turns. Expected n turns. And the nice thing about this is you can factor it. You have linear algebra. Linear algebra plays nice with sums. For example, you can pull out this big old thing like that. You can put brackets around that, do this big sum over here, and then at the end multiply by this vector. That would be perfectly fine. So to know what this number is, this is some honest to goodness number. Let's figure out what it is, and we're going to put it in the computer. We already have the matrix P in the computer from last class. We're going to put it in and add it up and see what we get. Question?
So much simple question. So on the normal geometric series sum,
Yeah.
we of course have the condition that the range has to be the absolute value of the range, it has to be strictly less than 1.
Yes.
So what's
Very
the
good.
equivalent for the matrix?
Yes, the equivalent is that all the eigenvalues have to have absolute value less than 1. And in fact, for probability transition matrices, all the eigenvalues are always less than 1. So it will always work. Yeah, great question. Okay. Okay, actually that's a lie. There's one eigenvalue whose absolute value is exactly 1, which is 1. 1 is always an eigenvalue, and it always has eigenvalue 1. And yeah, all the other ones are less or smaller. Fantastic question.
That doesn't cause
In this case, it doesn't cause problems because we zeroed it out. You'll see exactly what's going on when I type it in the computer. So this infinite sum would be infinite if you counted the last square, because you'll see exactly what I mean in a second. Yeah, I'll answer your question in 1 second on the computer. It'll be nice. Any other questions? Okay, let's compute this on the computer and see what it looks like. So I have what we were doing in Colab last time. Oh no, those are the answers. Okay, I don't want to show you that. Okay, I got to show you what I did in class. Okay, let me find that. Which I put a link to what I did in class last time on the CourseLink website, so you can also follow along there. It should be like view only, so you have to make your own thing. That's not the right one either. Let me try one more time. Okay, yeah, here it is. Okay, so this is what we did on Tuesday, and yeah, and today we're taking the matrix P. So let me rerun everything. So last time we were calculating the expected value of the position. So we used this V, which was 0 to 9. And we were saying, where are you on average, right? And we were figuring out, after one roll, you're at position 4 on average, and that kind of thing. And today we're answering the question, how long until you get to the end? And it turns out for how long you get to the end, you need the vector V is going to be this vector. It's np.array. It's not 0, 1, 2, 3, 4 like it's being suggested to me. It's 1, 1, 1, 1, 1 all the way up to with a 0 right at the end. That's the vector we need. So you sort of 1 point every time you're not at the end, 0 points if you're already done the game. How would you type this into NumPy in a smart way? I'm going to make an array of all ones, np.ones of shape 10. So that'll make an array that's all ones, hopefully, of shape 10. And then I will set the last entry to 0. The last entry is the 9th entry, v of 9 equals 0. That will work. There's also a trick you can do. If you put in v of -1, if you put a negative number here, it counts backwards, so it starts at the end. That'll say make the last one a 0. So that should hopefully make v all zeros. Let's see, v is v, all ones, and then a 0 at the end. Okay, that's what I wanted. And now I want to do this sum. So let me copy, and I did this nice code over here last class, where I did the sort of other half of this thing. So let's look at this loop. In this loop, we're finding the probability at time 0, and then we find the probability at time t. That's exactly what I have over here in my brackets, right? So these big giant brackets over here, this 1, 0, 0 with p together, this is pt, the vector at time t. So I'm just going to add them all up before we were finding the vectors one by one. If we add them all together and then take it with v, we'll get the answer we want. Let's see what happens when I add them together. Right, so in the code right now, it's just calculating the probabilities. We don't want this expected value. Let me just do the probabilities, and let me add them together. So I'm going to say running total, and that's going to start out as all zeros, and then I'm going to add it on. So let's say running total plus equal this thing, and stop giving me bad suggestions, Google. Okay, and let's print out the running total. Okay. All right. So let's look at what this is saying. So at t equals 1, you do one step of the Markov chain. You are, where are you going to be? Actually, let's start at t equals 0. How do I start at t equals 0? I guess I do this first. Running total. And let's start at 0. Okay, there we go. So at time t equals 0, there's a 100% chance you are at square 0, where that's where you are. So it's a sum of one thing. At time 1, it's actually a sum of two vectors. So you have the 100% chance of where you were at time 0, plus there's a 1/6 chance you're at all these squares. We've seen that a bunch of times. So the running total is the sum of this plus this. Then you add on another one. Now you've spent even more time sort of up here. Look, you've already finished the game sometimes, right? After 2 steps, you've sometimes finished the game. after 3 steps, the amount of time you spent over here in square 9 is also going up. And it goes up and up and up. Let's keep adding it up. Let's do it 20 times. So what is the pattern? All the numbers are always going up, right? Because we're adding probability vectors, right? The probability vectors are always, there can't be negative, probabilities can't be negative. We're adding them up. Every individual number is going up and up and up. And in fact, all of these individual numbers, they have a very nice interpretation. They're the expected number of times you were at that square, right? How many times were you at square 0? You were there exactly 1 time. Okay, so that's 1. How many times were you on square 1? Well, there's only one way to ever get to square 1, which is to roll a 1 on your very first roll. And then you'll be on square 1 time, and then you will never see square 1 ever again in the game. And that's because the snake only takes you back to square 2. So you actually might spend a lot of time on square 2 because you keep coming back there when you hit the snake. And that's why this is 0.56. And you'll notice it's going up, right? The longer the game goes, the more time you spend on square 2. It sort of has reached an asymptote here, though. It's getting closer and closer to some final number. That's what it is. All these numbers are slowly increasing. One of these numbers is increasing the mostest, and that is square 9. Square 9 sort of goes up by 1 on average. And that's because if you're already on square 9, then you'll still be on square 9, so it'll go up by 1. So if you have a large chance to be done the game, then this will just go up by 1. And in fact, if I run it like 100 times, you're going to see what happens. It's not going to change very much. Let's do 100 times. Okay, so what are these numbers? Well, the numbers for being on square 0, square 1, square 2, square 3, they're about the same as they were before, but now you've spent 96.6 turns on square 9. So if you play Snakes and Ladders 100 times, on average, you're going to spend 96 of those turns on square 9, the finished square, and you're going to spend like 1 or like 0.5 on all the other squares. That's how long you spent on each square. What is the total number of turns it took? Well, it's the inner product of this with the vector 1, 1, 1, 1, 1 that we saw before. So if I now do code running total at, remember at, v, that's what we want. And it's 3.37. That's how many turns it takes until you finish our little dopey Snakes and Ladders board. 3.37 is exactly 1 plus 0.17 plus 0.156 plus 0.29 and so on, adding up all these numbers, but please don't add up the last one. If you add up the last one, it's not going to converge to anything. So this is the answer to Gabe's question. When does this sum converge? This sum will converge as long as you don't include the last square. If you include the last square, then it'll go to infinity, because including the last square means it goes up by 1 as you go. But all the other squares have the chance of being on all the other squares goes down to 0. So this probability vector PT, let's say it this way. All entries go to 0 except entry 9. So all the entries go to 0 except entry 9, so you can add it up. And it's a good thing we put a 0 there, otherwise it would blow up. Yeah?
So in a more general case, if B is a matrix describing some other random Markov chain,
Yeah.
would the sum conversion for exclude if these states correspond to the, if the vector was 0 for every absorbing state that we have?
So you either need 0 for all the absorbing states, and there are some absorbing states. If it has no absorbing states, it can just like go around, and then this won't converge. Actually, we're going to talk about this more and more. So this it turns out this is like a big part of the course. So later in the course, this will not be the number of turns; it'll be the expected reward, right? And you'll be training your little robot, and you'll try to make your robot find out how to make its reward as high as possible, and you're going to use this formula to find what is on average the reward of the robot. And you want to make sure the robot, it's a very important point, you want to make sure the robot doesn't think it's getting infinite reward. So we're going to see lots of ways you can make sure this is finite, and when is it finite, and so on. It is definitely true, though, if you have a Markov chain that like sort of eventually ends, then it's very reasonable that it should be finite. Snakes and Ladders is a great example. It has that ending square. If you get to the end, no more. This eventually ends when you get to the end, and then it's over. So very reasonable that it should work. Okay. Great question. Anyone else? Yeah.
So you could actually solve it analytically by diagonalizing E.
Yes.
Okay.
Yes. Actually, you'll see. We're about to do that. Okay, but we're actually we're not going to diagonalize it. Let me tell you. Let me do one other thing. Let me do. So I pulled out this vector. Why don't I pull out both vectors? So 1, 0, 0, 0, and then I have the sum from t equals 0 to infinity of p to the power t, and then I have 1, 1, 1, 1, 1, all zeros. Okay, so this is like in linear algebra land, if you have sums, you can change the order of the sums. It's still equal. So this should still be equal to what it was before. And now, let's take what we learned before. What is the sum of a geometric series? The rule is, it's 1 over 1 minus whatever the thing is. So there should be, this should just be equal to 1 over 1 minus p. And you're like, well, you're crazy. You cannot do 1 minus a matrix, right? Okay, you have to remember, in linear algebra class, you don't do 1 minus a matrix. What do you do instead of the number 1? Yeah. Identity, exactly. So you do identity matrix. Okay, and in linear algebra class, you don't do 1 over something. What do? The inverse. So actually, you can do this 1, 1, 1, 1, 1, 0, 1, 0, 0, 0. And this is like almost true. It's not quite true, but it's like very close to being true. And the next thing we're going to do, we're going to actually show why. We're going to derive an equation that gives you this as the answer. So this is the formula for the number of turns, n turns. And what we're going to do is we're going to find an equation, and it's not going to be identity minus p inverse. It's going to say something like a equals p times a, right? And then if you solve the equation, it's like doing this. We're going to see that in a second. That's going to be a big part of the course. It's called the Bellman equation, which is a big, important equation. Okay, so this is what we want to do, is we sort of like want to make the infinite sum into an equation and then work on solving the equation, and that will give us the infinite sum for us. We could just start doing it. But again, the best way to learn math, when there's a hard problem, find an easier problem. And we're going to do it with the geometric random variable again. So we're going to see, is there a way we could have done the geometric random variable without an infinite sum that would have directly given us this 1 over p answer by just thinking of an equation that this number has to solve? That's what we're going to try to do. And then when we learn how to do that, we'll apply the same logic to the Markov chain, and we'll see this number has to solve an equation, and we'll see it's this equation. This is like the solution to the equation. Okay, so that's our goal. So again, we're back to the easy problem, which is the coin flip, and we say find an equation that expected value of g, a geometric, solves. Okay, here is the simple equation. So and here's the observation. If you're flipping a coin and you're like, how long is it going to take until we get a heads? How long will it take? Well, you flip your first coin, and one of two things happens after you flip the first coin. So with probability p, something happens. And with probability 1 minus p, something else happens. So you're sitting there, you're flipping your coins. If you get a heads on the first flip, then you're done, right? If your first coin flip was heads, then you're finished. How long did it take? It took 1 coin flip. So if you get a heads, it took 1 coin flip. How long does it take if you got a tails? Well, you could say, oh, I don't know, it's like random. But it's random in a specific way. It takes 1 longer than if you were just starting from scratch, right? So you're sitting there like flipping coins, and if you flip a tails, then you're like, okay, well, we used up one coin flip, but now I gotta wait some random amount of time, and that random amount of time is also a g. Okay, it's not the same g, so let me write g tilde. G tilde is another copy of g. Another, let's say, independent copy. Okay. And this is a really big idea, which is that you can relate the random variable to itself, right? If you want to know how many coin flips it's going to take, well, it's going to take however many coin flips it takes after the first coin flip, plus, and then like you're in the same situation again. And this is like, it seems like I haven't made any progress. I've written g in terms of g tilde, but g tilde is the same as g. So have I solved anything? I have the thing I wanted, and I have the thing I wanted. Like, what am I doing? But this is like the beauty of algebra, right? Like you can, if you have the thing you want on both sides, you can solve for it. So now take the expected value. Take expected value of both sides. On the left-hand side, you get the expected value of g. How do you take the expected value of the right-hand side? Well, with p probability, it's 1, so that's a p times 1. P times 1. With a 1 minus p probability, what do you get? Well, you get 1 plus g tilde. On average, what is that? It's 1 plus expected value of g tilde. Okay. And now this is an equation we can solve for. The expected value of g, what is it? Well, I don't know what it is, but whatever it is, it satisfies the equation. It's equal to p plus 1 minus p times 1 plus expected value of g tilde. And g and g tilde, even though they are different copies, they're independent copies, they have the same average, right? So these have the same average. So now I can just rearrange the equation. Let me simplify it a bit. P plus 1 minus p from the 1 plus 1 minus p times the expected value of g. Okay, and I'm not writing tilde because g and g tilde have the same average. Okay, so now it's like 5th grade algebra, we solve it. P plus 1 minus p is 1. Move the 1 minus p to the other side. You get 1 minus p times the expected value of g. And then you solve it. And the expected value of g equals 1 over p. Right? So you have p times the expected value of g equals 1, and therefore it's got to be 1 over p. No infinite sum needed. Right? This is like the beautiful thing we did. All right. Questions or comments about this one? This is sort of Markov way of thinking about things, right? You have what you have now, and whatever happens will lead you into a situation that is similar to the situation we're in now, right? And in fact, this flipping a coin problem, you can think about this as a Markov chain with two states. There's still flipping, and there's I'm done flipping, right? And I'm done flipping is the terminal state. It's like a snakes and ladders board with two squares. You start on square 0, and if you flip a tails, you stay on square 0, right? So this was exactly what we did. This is snakes and ladders with two squares. With two squares. But yeah, so you got square 0 and you got square 1. Square 1 is I'm done. And square 0 is still flipping. And we use the fact that, like, you know, if you flip a coin and you're not done, it doesn't matter how many times you were flipping, you're still in state 0. That's how we did it. So now let's think, how are we going to generalize this to more squares? So this is the idea that's going to lead to our equation. Generalize this to more squares. And let's see if we can come up with an equation like this. So I got the number of turns, that's what I want in snakes and ladders. And what I did for g is I wrote it like this. I said, okay, with some probability you're done, right? You just like, you flip it right away. So that's if we finish. If we finish immediately, then it'll take one more turn. What if we don't finish immediately? So you roll the dice, you didn't finish. Can we say it's 1 plus n turns again? Otherwise? Does this make sense as a thing? So you're playing snakes and ladders, you're like, how many turns until I finish? We roll the dice. If we finish the game, great, then we're done, it took one turn. If we don't finish the game, is it true that it takes one turn longer than what we started with? So you do however long it took before, you just add 1 to that. I guess with a tilde, okay? What do you guys think? So yeah, some people are shaking their head. Why is it not quite true? Yeah.
Because you could be in a different state.
Yes, you can be in so you've made some progress, right? It's like we started at 0. Even if we don't make it all the way to 9 right away, we made a little bit of progress. Like, you got to give us some credit for the progress we made. Okay, how are we going to incorporate the progress we made into our little thing here so that it works? So n turns is what we want. It's the number of turns it takes starting from 0. But if we just use n turns, we can't keep track of like making progress. So how can we modify things so that we keep track of how much progress we made, and then we can like give ourselves like credit, like you like got a good roll over here, so it should take like less turns than we started with. Like we've made a little bit of progress. How would you do? All right, everybody brainstorm for 2 minutes, and then tell me your best idea, and then we'll go home. 2 minutes. Okay, I'm gonna make a word cloud called "Tell me your best idea." It's coming. Add word cloud. Okay, there it goes. Tell me your best idea. All right, there's like 10 seconds left. If you have no ideas, then your best idea is I don't know. But put in whatever you got. So I know you were still here at the end of class, and I'm curious to see if anybody has the idea here, which is truly, truly a beautiful idea. Okay, let's see. Did anybody have any good ones? All right. I don't know. Okay, great. Yes, okay, this actually, the most common idea is exactly the right thing, which is you need to include where you're starting from. The thing we are looking for is n turns starting at 0, right? Starting on the 0th square, how many turns will it take? If you try to make an equation just for the number of turns starting at 0, you cannot do it. But if you make a joint set of equations for the number of turns it takes from all the squares, they all depend on each other, right? The number of turns it takes starting at 0, well, with a 1/6 chance you end on square 1, so it's going to involve where you're starting from. This is the idea. We're just going to include where you're starting from. And we are going to end up with some stuff. Yes, okay, I need to stop looking at this. Okay, this is the big idea, is we're not going to do the number of turns. We're going to think of the number of terms depending on the starting point. We're going to add in from state 0. And that way we can give ourselves credit. When you roll at something, it will be the number of turns starting from the state you ended on. So it'll be from state, I'll call it S prime, and then if you go to state S prime, if you move to S prime, right? So if you finish right away, then you're done. If you don't finish right away, it's going to take you some amount of time, and the amount of time can now depend on where you are. And actually, the left-hand side of the equation, this thing is a vector. The right-hand side is it's a combination of all these things. It's also a vector. And when we take the expected value, we're going to get a linear combination of all the different things. So when we do the expected value, we will get a matrix vector system. So take expected value, and then we will get something v, and we'll get something pv over here. With details that will come next class. So that's the idea. Don't keep track of just one state at a time. look at where you start from, and it turns it into a vector, and that vector depends on itself. Okay, we're going to do that next class. Have a good weekend. You do have everything you need to do all of the assignment now. So the assignment, one of the questions will involve you doing this big infinite sum, but you know how to do it now. You saw me do it. And you'll answer a question where the answer is similar to that 3.37 that we got a second ago. But you know how to do everything now. Feel free to post on the forums if you have any questions or send me an email. Okay. Have a great weekend and see you guys on Tuesday.